So last class we looked at MVA, right, which has computational complexity that depends upon n, right, the number of customers in the system, and as we said, as we saw, right, that can be very time consuming, especially for very large systems. Then this becomes a problem, right. So there have been several approximations, and this is an old approximation called Switzer's approximation. There are several others that are being proposed, but since this is there in the textbook, we will just use this as an introduction to how we can do approximate. So here we replace that recursive definition with a iterative definition of how to do this. Okay. So this is the so called Switzer's approximation. So the basic premise is that, which we can argue, right, as n increases, right, then the Qi, the number of customers queued in a particular queue is also going to increase, right. And then what he is assuming that this is that the rate of increase, right, so Qi by n is basically assumed to be a constant, some constant Ai, right. So it is assuming linear relationship between the number of customers queued at a given queue to the total number of queues, right. So if I make this assumption, then I can simplify, and then, right, then we try to come up with it. Okay. So therefore Qi so with n minus 1 customers this is the ratio, and then with n customers this is the ratio, right. So that implies Qi of n equals n by So that is the basic expression that you are going to use for Qi of n. The previous case it was we used Qi's in right at the end of the expression, right. We computed R of n, then we computed R, then we recomputed the Q's based on that, and this we kept repeating. So let us see how this looks like. So now our response time, right, Ri is now Si into, this was Qi of n, right. So instead of Qi of n I am going to replace this with the that is okay. I had written that the other way around, it should have been Qi of n minus 1 equals, yeah, right, because in the original expression we had Qi of n minus 1, I am simply expressing that in terms of n again, right. So Ri of n simply depends on Qi of n with this approximation n minus n by n. Right. Previously we had equals 1 plus Qi of n minus 1, right, that is the number of customers that I had with n minus number of jobs queued at Qi when there were n minus 1 customers, right. So again refer your previous, your Ri of n was Si, right. This is what we used last time, so that is where the recurrent that your recursive, this is again for your fixed capacity, and it is simply Si in the case of a delay center. So instead of this qi n minus 1 I am using this expression. So now n depends only on n, does not depend on n minus 1, right, or Ri of n does not depend upon qi of n minus 1 anymore, simply qi of n itself. So this is the simplification. So what we do is we start with some random value for qi and then iterate with this value until you converge at some point. And again this proof of convergence is not there, so and also depends on the initial value. The time to converge depends upon your initial value for q of I, and convergence is also not guaranteed, but what people have done is they have just tested it empirically with different systems and found out whether this is converging in less for large n's in particular. If I use n equals say 10,000, if I can converge in 100 iterations, that is still better than converging in requiring 10,000 iterations with the original, with the exact MVA. So that is right, the previous one is your exact MVA, this is your approximate MVA. Is that clear what you are trying to do? So the actual algorithm will now look something like this. Okay, so your approximate MVA, so initialization is that your throughput is 0, and then for since there are m queues, we just need qi, and I am simply assuming that the n jobs are evenly distributed among the m queues. So this is my initial assumption. I could use anything else, but I am just, you could put all the n jobs in q1 if you want and let others to be 0, but I am simply assuming that they are all evenly distributed across all the queues, which is incorrect, right, because you know that some queues will be larger, will be having more customers than other queues. Okay, and then you have your, so now it is a big while loop, and then we will initialize this, so some initialize epsilon to some number, right, this is your termination condition. So when you converge, your qi should equal to your xRiVi, okay, what was previously. So in this case qi is the initial value, right, that will certainly not equal to xi because x is 0 initially, right. So as you keep updating, so this is the case for the difference between your actual q, right, value that you are computing, and that is with the two different expressions you are computing your q values, and I look at the max value, right. So the max difference between these two expressions for q length, if that is I guess greater than epsilon, I keep looping. Okay. I am sometimes using C syntax, sometimes I am using simpler syntax. So Ri, again these are all arrays, right, is simply 1 over so this is your updation of Ri based on the previous value of qi, and then I compute R, which is that, then I go further and compute x, which is x n by up to z. Then I have to update my QIs, right. That's kind of funny, right? So does it look funny to you? So I am recomputing QIs, which is equal to XBI RI, and that's, so where is the condition will terminate. There is something in the example that we are doing differently. It should be the other way around, right? It should be QI, it is to QI and then the previous iteration of QI, right? The previous iteration Q value and the current iteration Q value should be converging. Because this I am just assigning Q, right? Okay. If it is do while, then no, even then you would have the update here. So unless I have Q dash and then QI, right? So the previous computed Q and then this one should be different. Yeah. Okay. Yeah, that is what the example is trying to do, but the code is got that flaw. Okay.
So why are we taking max of I?
I want to make sure that the largest difference between the previously computed, right? So if I were to update this, I would keep that as QI, right? And then
but QI will be,
yeah, let's I have to basically store the previous value of QI in something, some temporary variable, right? So if I keep this as QI, then I should replace this with the QI dash. Before I calculate, yeah, I should be before, yeah, okay. So let us try to do this, okay, let us do this as well, QI dash I do not have here, right. If I replace this with, I need something for QI dash. Okay. So let me just, you know what changes I am trying to do. So I will assume that QI dash equals 0, right, in the init, and then I simply search, or right, this is what I am max of I while this is greater, okay, this condition we will have, and then later on at the end, before I do my does it make sense? So just keeping the previous value of QI and then looking at where the QIs are converging, right. I am doing everything as before, right, the same while loop. I had my QI equals, right, n by m for all I, this is what I had before. We computed Ri, we computed R, we computed X, right. Once we do all these computations, I am just saying let us store it locally. If you are not convinced, when you implement it, you will get convinced, okay. So we look at the example when this will be clear, right. The example has it correct, not this piece of code. Okay, so let us go back to our previous example. Gosh, the book example, by the way, for this is actually all the values are incorrectly computed, so you should make a note of that. Okay. So example of the same example we saw before, right. So we had SA was service time of the CPU was that, sorry, that is the 2. So what were the visit ratios? So this is 10, 5 and 16, remember 10 visits to disk A, 5 to disk B, and therefore CPU was 16, the same thing we did last class. And then the DAs were 3, 1 and 2, this is S as in seconds. So mostly we just look for this, right. This is pretty much all that you get, SVN, after that you can get the D. So now the first step is to find out R, right, you need Q before you can find R. So initialization, I said we will use Qi dash equals 0 and then Qi was n by m and n we said was 20, right, m equals 3, 20 by 3. So therefore we pretend that initially each queue has 6 customers, 6.67 customers, that is our start for the iterations. So first iteration, okay. So what is R CPU equal to S CPU into 1 plus Q CPU into n minus 1 by n, right. Oh, okay. So what is this equal to? Is that right?
So can we calculate also the QCP? We have got SA, B and D. Instead of directly taking n by n,
Okay.
we can calculate also.
From how? Where?
Laws which we do.
This is all that you have. So to compute your Q, you need to know X, right? We have X RI VN, right? So you do not know the throughput, nor do you know the response time. That is what you are trying to compute step by step, right?
That is a pretty strong assumption that QI will be n by n.
That is a simplifying assumption. If it converges, it will converge regardless of the initial value of this. You can also, like I said, right, give n equals put all the n jobs in the first queue and then see what happens, right? The system really converge after that or not, but at some point it should converge. So what is the answer? 0.91. Okay. So the book was wrong and I was also wrong in my computations. I also ignored the fact 19 by 20 was ignored. So the book actually has this as 1 plus 6.77, can be 6.77, right, 19 by 20 into 1.6.67. Okay, let us compute the next one. RA is,
Sir, when we are taking this Q CPU 6.67, basically we are using Q of n.
Q of I.
Q of I.
Yeah, this one.
We are not taking n minus 1.
It should be?
Yeah, it should be n equal to 1, right?
It should be?
N equal to.
N equal to?
See, the original recursive form was taking, it was keeping on adding one more customer.
The previous one, yes, yes. So in this case it is just QA of, this is 1 plus QA of n minus 1.
Accommodated, and we are trying to compute.
No, I am assuming that out of the all the 20, right, there are 20, I am starting off by saying that they are evenly distributed among all the 3 queues, and then I am using that value to keep on recursive, so that right, so instead of using q of n minus 1 I am using qn itself as my recursion for iteration, sorry, right. No, that is input, no, that is input. In such cases you want to look at the throughput if there are 20 customers in the system. This and the previous case again my goal was to find for n equals 20, but I had to start from n equals 1 and I went step by step, right. So until n equals 20, so that is if you have n very large, then you will have order n running time, right. So therefore you want to reduce that by iterating on the with some approximate value, and then you keep updating this value until you converge on some QA values that do not change beyond a point. The initial value of q, no, n is an input, n is not initial value, n is an input.
Some initial value where we start.
Initial value is for the QI. You need some starting value. So this is going to be SA, which is 0.3, 1 plus again. And what is this going to be? Two point two. So in the book the values are correct, but the expression is not correct. Okay. The same as before. So what is this going to be? (2.2) into 2 by 3, 4.4 by 3, 1.467 to 1.47. R. Okay, 44.0085. So we will stop 44. So this is the overall response time of the system, right. So now the throughput is 20 by, I did not specify Z, Z was 4 last time, right, yeah. So remember that Z equals 4. So 20 by 44 plus 4, 416. So now I am going to store my so I will just store the current values of Qi in this Qi dash, and then I compute the new Qis, right. So now I know my x, we know we have computed Ri, right. So I can go back and recompute this. So this is point, is it 0.416 into 16 into, oh sorry,
6.11.
Ri was 0.92. So we have from 6.67 we have recomputed Q CPU to be 6.11 and QA is likewise 0.416 into 10 into, we computed this to be 2.2. So this was 9.17. So that is our first update, right. So where we started with n by m 6.67 for all of them. Now because of the fact that this disk A is got a higher service time, you are finding that the system is saying that there will be more jobs in disk A than in the other two queues, okay.
But it does not 93 to 67. It should total should come to 20.
Total should come to, does it come to 20? Some approximation, yeah, some things are missing, but should come to roughly 20. Is it 9? It's coming to, yeah. But there is also some amount of time in thinking, right. So there is z equals 4, right. So what is happening is your probability of jobs being in think state is 4 divided by 44 plus 4, R is 44, 4 is, right. So probability of job being that is 4 by 44, 4 by 48, that is 1 over 12, and that is 0.8, that is the missing 0.8. Okay. So now I look at, right, the delta Q, which is max of 6.67 minus 6.11, and then we had 6.67 minus 9.17 and then 6.67 minus. So this happens to be, which is still greater than epsilon. So these are the new Q values, okay. So one more iteration with the new Q values, recompute RFI, recompute everything, okay. So after the second iteration, I will just give the results, it is kind of right. So our CPU gets recomputed to be 0.85, RA gets to be, actually RA is upward revised, RB is 0.78, okay, and then R itself is 44.64 seconds, the X becomes 0.39. So this is the same computations repeated with the new values of Qs. Questions? 0.39, that is the revised X, yeah. Sorry, this is 46.64.
Just correct that XRA there you can write as QZ.
Yeah, but if you simply say QI minus XVRI, then since we just updated QI, if I simply use my program as such, right, I have just updated QI equals XVRI, then I cannot go back and say QI minus that is going to be greater than epsilon.
We can just use some other variable.
Yeah, that's yeah. So you need something to store the old value. Yeah. Mathematically you can say that, but when you write it as a program, you have to make sure that that is captured. Okay. So after this X computation, we now recompute the Q CPU to be 5.38, QA to be 11.5, then QB to be. So you notice that, right, there is more and more Q buildup that is happening in QB, or which means our initial estimate was totally way off, right. So this is your second iteration. So you repeat this with a little program, and the book finally shows for n equals, or for the 16th iteration, actually you are sort of converging on the Q lengths, which is kind of silly because my n was 20, right. So but if you choose maybe n equals 100, you probably might have converged again in 16 iterations, right. So really the unless you have a solid proof that it converges with significantly less time, this might end up taking much longer than simply running it n times, right. So finally if you look at the 16th iteration, then the R is going to 56.63, X is settling at 0.33, right. This we knew from last time, that is our upper limit 1 over D max. So X is finally converging, and then the Q lengths, actually it is so our total initial estimate was totally way off, right, assuming that that is equally distributed across all the Qs, because QB was actually 0.48, so it took a while for QB to come down to 0.48 and QA is 16.42. So the initial value makes a difference in your computation, right. So if you want to be really more efficient, you could probably look at the service times or demands, right, for those 3 Qs and use that as use simply a di by sigma d I, right, would give you a better approximation. If I say that if it is proportional to the demands, right, the amount of time number of customers queued is going to be proportional to the demand on that queue itself. So you can maybe use that, right, because the demands are 3, 1 and 2, so you know that the queue in this case is going to be larger than the others, right. So I could have simply said 3 by 6 and so on, right. So you could have used different start estimates for all the QIs, right. So for example, I could have said that QI simply right QJ. So in this example, this would have been Q CPU would have been 2 by 6 that would still be incorrect, it will be 40 by 6, which is actually turning out 1.78, but anyway maybe this will give you less iteration, so that we can verify with computers, okay. That is approximate MVA. So this is exact and approximate MVA. Questions before we go to something even more? So this is only still mean value analysis, right, only getting the mean Q lengths. For example, if I ask you what is the distribution of the Q length right, a number of customers at a particular queue. We know that for MM1, right, we know that for MM1 queue the number of customers, probability that there are 4 customers in the queue is what, rho I into 1 minus rho. So we know that from our MM1 results. We want something similar in this case, so that is the next step. Now we will now move to what is called, we will exact right, more detailed analysis, not just the mean analysis. We would like to know exactly the number of customers, so the distribution of the number of customers at each queue, and then do lots of analysis based on that. Okay. So I am skipping one part of chapter 34 right now, that is the balanced job bounds. We saw the bounds last time, right, 1 over Dmax and so on. We can improve that, as I said, but I will skip the derivation of that to after I finish this convolution algorithm. Okay.